Hello everyone. In this video series, I will be doing a column example in MIDAS. In the first few videos, I will be showing this example, how we model it in MIDAS, and how we use the design functions within MIDAS to give us a quick summary report. And then I do want to create a follow-up video where we can dive deeper into the detailed calculation that MIDAS provides. And here I have a hand calculation just to verify the slenderness effects that MIDAS calculates and how it relates to ASHTA. It does differ slightly, but it is almost exactly the same. Now going back to our example, we will be doing a circular column, 3 feet in diameter, with a height of 25 feet. For the longitudinal rebar, it will be 12 number 9 bars. For the shear, it will be number 3 spirals at 4 inches. Our concrete and steel properties will be 4 KSI and 60 KSI. The elastic modulus and the elastic modulus concrete will be 29,000 KSI and 3640 KSI. Now for our loads that we will apply in our model, in the longitudinal direction, we will have an axial load of 1,000 kips, a permanent moment of 100 kip feet, and a moment that results in side sway of 600 kip feet. The transverse direction, the same axial load, but now it will be 80 and 200 kip feet. And the reason why I wanted to do a permanent and a total moment was to show how MIDAS and with our hand calculations, how they calculate the permanent over total ratio and how it's used to calculate the slenderness effects. Okay. Additionally, I also wanted to provide here the fixity. I want to provide two different fixities in each direction so that we can manually change these parameters in MIDAS, and we can show you how we do that. Okay, so now we move on to MIDAS. Now that we open MIDAS, the first thing we want to do is first check our units. The problem was in kip feet, so here we have kip feet. If you don't have the two tree menus open, just simply right click here, tree menu 2. Okay, so first let's start by creating our nodes. Let's create our first node at 0, 0, 0. The height was 25 feet, so Control Shift S, select it. We want the other one 25 feet above the first one. Now we can define our properties. Let's start with our material properties. Click Add. We're doing concrete, and we set 4 KSI. So let's click 4,000 PSI here. Click OK. It will show all our section properties and material properties. Click section properties, and now let's define our circular column. Scroll it around. Let's just name this column. And it was, let's select user so we can manually define him. It was 3 feet. Okay. Now that we have defined both, since we're not using them yet, they'll show in blue. But once we create an element and define it using these materials and section, let's connect the first node to the second node. Now it will show in black because it is defined. The next thing we want to do is define our boundary conditions. So we will just fix it at the bottom for this example. All directions, select our node at the bottom, click apply. There we go, it is fixed. Now let's move on to apply our loads. Let's go to loads. To apply both the axial and the moments, you can do that just under nodal loads here. Click nodal loads. This is empty because we haven't defined any load case yet. So let's click the 3 buttons here, the 3 dots, and let's define our first one, permanent. Make this one the dead load. Click add. And then the rest, we can just name it others for all other loads. And then let's just make this a user-defined load. The load factors won't really matter because I am using already factored loads in the example. So under permanent, let's just double check our loads. We had 1,000 kip and then 180 because we're just checking. We just want to apply the permanent ones right now. So 1,000, 180. Z direction, make sure we click negative so it could be acting on the pile. negative 1,000. Not on the pile, on the column. Here we have 100 in one direction, and then 80. Since it is circular, you will see that it doesn't really matter which direction, but usually you do want to check your axis, your global axis, to make sure you're playing it in the correct direction. Let's just select our top node and click apply. See the arrows there? And if you want to display the values, that's why I like to have the tree menu 2 open here. Just right click and click display. There we go. Now let's also add all the other loads. We won't add the axial load here. Problem 600 and 200. 600 and 200. Here, click apply. Let's undisplay the first one and then just display the others load. There we go. Now that we have everything defined, let's see if our model runs. Click run. And there we go, ran. So now, if you do want to see any analysis results, not the design, just results, we go to the results tabs, and here we can see any reactions, deformations, any forces, any beam diagrams. Let's just show our moment, values, and the legend. Legend, so we can see the fixed values, not scientific notation, and that makes sense. What I really wanted to show was design within MIDAS. So that is what I will go on to next. To do that, we will go to design, and it will be here under reinforced concrete design. And here you see we have all our codes. Let's just use the latest code. I don't have the latest MIDAS, so that's why it doesn't have the latest code, but let's just use LRFD17 for now. And where we want to define our longitudinal rebar is here under column section data for checking. So let's click on that. We'll click on our column, which will automatically show here since we already defined it earlier. And here's where we will input all our info. So let's go back here, 12 number 9 bars and number 3 spirals at 4 inches. Since it's in inches, let's just change it quickly to inches, and then I'll open it up to make it a little bit easier. Click on it again. Spirals, number 3 at 4 inches. And for our longitudinal rebar, we can put the number here, 12, number 9, now number 10, number 9. And then here we put our cover. Let's say 3 inches for this problem. Click add. Now we can click it again, and it will show right there. Now, there are a few more other things that I want to show before we move on to the actual design. But let's just, and these we can modify after or before, so I will quickly run the checking, column checking. Oh, and you see here, we actually have an error. So error checking, I didn't input the load combination for checking. So in order to do that, we will go to results, go to load combinations, and we have to actually, in order to run the design, we need to put our load combination under concrete design. So let's just say load combination 1. And since they're already factored, let's assume it's already factored, let's just keep the factor of 1. Now, able to run. Here, if you click the member, we have click graphic. Here is our summary report that I wanted to show you. This will have all our design condition input. So our height, it's still in inches. Actually, let's just keep it in inches for now. But we'll have 300 inches. It will have our concrete strength, yield strength, steep rebar strength. We'll have our total area of our reinforcement. And then here we'll show our applied loads. They are in inches, so mind that. Then here we'll show our interaction diagram with our DC ratios for the biaxial flexure. Everything's okay, so we do not need to increase the number of rebar. And then here it gets plotted, the total curve, and then our loads. So it's okay. We didn't apply a shear force, but if we had, here it would provide the DC ratio for it. But we actually did show the spirals. So it is providing shear strength by rebar and shear strength by concrete. Okay, let's just close this real quick. And now in the following section, I will quickly go over how do we take into account the length factors, right? Because our problem, we had two different fixed conditions. So I just quickly go on to that. We'll go to, in order to update that, we go to common parameters, and here are a couple of different sections. I'll just show you a couple. In definition of frame, and this I was going to go into detail more when I do the detailed calculations. If you do want to define it as sway or non-sway, this is where you do it for your definition of your frame. And this will slightly change some of those equations. I'll keep it as unbraced for now. And then let's go over our effective length factor. So now is where we can apply our effective length factor to take into account those conditions. So now let's quickly look at the code to see what we should use for these values. Here are our conditions, and I have included here on the next page a screenshot of the code. So in that one direction, we have this condition here, where it's highly rigid at the top and the bottom. So let's assume a design value of 1.2. Now, in the other one, it's free cantilever, so it's condition E, and we will assume 2.1. And in my calculations that I'll show in the second part, I will also show where we use these in the calculations. But for now, let's just apply that in MIDAS. 1.2 and 2.1. And this will slightly increase the moment. So that's why it's important to apply these. We do have to select. If I do this, let's just exit back to it. I just wanted to exit the results tab. Let's go back to design, common parameters, effective length factor, and let's apply them. 1.2 and 2.1. Select. Apply, and now it will show right here in the middle of your member. There we go. Now our design, we can open this, and it will be slightly different just for the magnified moment. Here is our updated results. So yeah, that is how you use the design function within MIDAS. In the next video, I will be going over how all these values are actually calculated and how the magnified moment that is used for the interaction diagram is calculated as well.